Good morning, team. Coming to you live. Well, no, it's not going to be live when you watch it. Coming to you very much not live from the Tuesday morning, 7 a.m. edition. We're just going to do some light exponential growth and decay, some rational exponents, and some exponential expressions to get us started. These are the examples that we had in our lessons yesterday, and I hope they help you get ready for Wednesday's quiz. So, exponential expressions are equations that are going to look like this. They're going to have unknowns up here in the exponent, and to solve these, we need to be able to apply our BEDMAS at a high level and use inverse operations. But as well, one of the key things is to create common bases. So let's take a look at how we do that here. If I'm going to answer a question like this, first thing that I'm going to do, add 5 to both sides, because I get rid of that loose addition and subtraction that's complicating the question. Then I get something like 3 to the 2x plus 1. There are sneaky, cheeky brackets hiding here. You have to do that first, is equal to 9. Then I rewrite 9 as an exponent, 3 to the 2. And that's 3 to the 2x plus 1 is equal to 3 to the 2. That tells me that 2x plus 1 must equal 2. So let's go down here, and then we will solve it. So if 2x plus 1 equals 2, then come on, x equals a half. All right. When I say come on, I mean you do your inverse operations and you say 2x plus 1 equals 2. Subtract 1 from both sides. 2x equals 1. Some number that when multiplied by 2 gives me 1. Well, that's x equals 0.5. X equals 1 over 2. Hooray! So that's, if we plug that in here, you check this in your calculator by doing 3 to the 2 times 1 half, because you sub in for x to check your answer. Okay, 3 to the 2, this is 3 to the 2 times 1 half is 1. 1 plus 1 is 2. And then you have 3 to the 2 is 9. 9 minus 5 is 4. Okay, so it works. All right, 4 to the 3x plus 2 equals 64. I did this in a funny way yesterday, but I'll do it the easier way now. 64 can also be written as 4 to the 3. Right, 4 times 4 times 4 is 64. And then 4 to the 3x plus 2. Well, 3x plus 2 must equal 3 then, right? 4 to the 3x plus 2. So then let's write that this way. 3x plus 2 equals 3. All right, subtract 2 from both sides. 3x equals 1. X equals 1 over 3. Done, final answer. Plug it up here. 3 times a third, that would be 1. 1 plus 2 is 3. 4 to the 3 is indeed 64. So it works. Okay, I think like solving checking your work is a great way to reinforce these ideas. Okay, so 256. Well, if 2x, sorry, oops, I don't have undo powers here. I need to do it this way. So here, if I know that 2 to the x is equal to 256, well, what's 256? 256 is 2 to the 8, right? So that means x equals 8. How do I know that 256 is 2 to the 8? Well, you could do this. You could go down, get your calculator going, and you can say 256. Divide by 2, and you count this way. Divide by 2 equals. 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 Okay, you count them. And then to the 8, okay, that's 5 plus 3 is to the 8. Okay, so it's to the 8. All right, you can just count the number of times you have to divide this by 2 in order to get all the way down to 1. And that would be the power of 2 that it is. Okay, so here, these are better questions. 32 to the x minus 1 equals 4 to the x plus 2. 32 cannot be written as a power of 4. It can be written as a power of 2, and so can 4. So our common base is going to be 2. So there, 32 is the same thing as 2 to the 5 raised to the power x minus 1. That's going to be equal to 2 to the 2 raised to the power x plus 2. Okay, so now multiply this out. 5x minus 5 is equal to 2x plus 4. What did you just do, Mr. Jennings? Well, I applied the distributive property, and I also skipped a step. I could have shown you that I can expand this like this and expand this like this because there are cheeky brackets hiding here and here. And what this is telling me, this is a set of instructions. Remember that x to the a to the b is equal to x to the a times b. Okay? So if that's true, then 2 to the 5 raised to the power x minus 1 should be 2 to the 5 times x minus 1. When I do this multiplication, I have to use distributive property. Same thing here. 2 times x plus 2, that gives me this. And so these things are equivalent. If those things are equivalent, then that is an equation that I can solve. So let's move all the numbers to one side. Add 5 to both sides and subtract 2x. So that would be 3x equals 9. This 5 moved over here. This 2 moved over there. And then we have this, and then x is 3. How do you do that? I divide by 3. Okay, I divide by 3 both sides. All right, let's keep going. So that's your final answer. X is equal to 3. And you can check it. 32 to the 2 is the same thing as 4 to the 5. That sounds about right. 32 to the 2 is 4 to the 5. Okay, I guess that's true. All right, cool. All right. I could check it on my calculator, but I'm positive that it's right because I don't make mistakes. I do make mistakes all the time. This one's trickier. 1 over 64. How am I going to deal with that? Oh, I remember this cool thing that if I have 1 over x to the a, that's the same thing as x to the negative a. Okay? The function of this negative here is just to throw this to the bottom of a fraction. So I can rewrite that as this is equal to 64 to the negative 1 if I want. But I don't want to write this as a power of 64. I would love to write that as a power of 4. I might have had to write it as a power of 2, but I don't need to. I can write it as a power of 4. This is 4 to the negative 3. Prove it to yourself. 4 to the negative 3 is equal to 1 over 4 to the 3. 4 to the 3 is equal to 64. Okay, so that's how you rewrite that. And then this is equal to 4 to the 2x minus 1. 2x minus 1 equals minus 3. 2x minus 1 equals minus 3. Add 1 to both sides. 2x equals negative 2. Divide both sides by 2. X equals negative 1. Check it. Negative 1 minus 3. This would be 4 to the minus 3 over here. And that's indeed 4 to the minus 3 there. Okay, that's how you do that. Okay, so then that's working with these exponential expressions. These are simpler examples than the problem set I gave you. Should we take a look at some of the ones from the problem set? I don't know if we need to do that. We have a couple other things to do this morning. So let's take a look at rational exponents now. Okay, rational exponents, everyone. Rational exponents are cool. Okay, they are exponents that are fractions. Rational means a ratio number, and ratio numbers like these are rational exponents. Okay, so we have a rational number as the exponent in a power here. And we can rewrite these with nth roots. Okay, so what's the meaning of an nth root? Okay, so here, I'll draw you a little picture. If I have a situation where I've got I need a pen. Okay, where I've got a cube, and I know the cube has a known volume. Say its volume is 64. Okay, this is volume equals 64. And then you say, well, if the side length were x, what would it be? Well, the only thing I know about x is that x to the 3 is equal to 64. How the heck do I solve that problem? Well, I take the cube root of both sides. So the cube root is something that looks like this. The square root actually has a cheeky 2 hiding in it, but a cube root has a 3 right there. And if you punch this on your calculator, the cube root of 64, it will tell you that that is 4. It will tell you, give me some number that when multiplied by itself 3 times gives me the number inside here. That number is 4. So that would, the next line in this solution would be x is equal to 4. Okay, those are cube roots. Cube roots. Now we can have any number there. And that would be, give me a number that when multiplied by itself n times is this number. Okay, so when we are transferring between these two forms. Okay, this is the rational exponent. This is a radical. All right, and this is an nth radical. So this number here goes into the radical, the bottom of the fraction. This number here can come in here. And to be honest, I prefer writing it this way. X to the a over b is equal to the b root of x raised to the power a. I find this to be a much more useful way of understanding this idea. Okay, let's keep going. So here you see another example of this, x to the a over b. This is the b goes here and the a goes there. It can also go, if I have this in a bracket here and I didn't write that there, I could have that out there. It can go in or out, however you like. So if we want to convert 27 to the 2/3 to radical form, well, we take this number and put it as the index number of the radical. Then we take this number, I like it out here, outside the brackets, and then I have 27 there. Now, the third root of 27, a number multiplied by itself 3 times gives me 27. That number happens to be 3. So this is 3 raised to the power 2, and this is 9. Okay, now reinforce what you're looking at. 27 to the 2/3. Okay, so it's less than 27 to the 1. 27 to the 1 would be 27. Okay, it's more than 27 to the 0. 27 to the 0 would be 1. We found a number here between 27 and 1, and it happens to be 27 to the 2/3. Okay, you can also reinforce what you see in the curve. And the curve, if I draw that in red, because that's an exciting color, it's going to come along here, be extremely close to the y-axis, and then start growing super fast out there. Okay, where it crosses the y-axis is going to be at 1. This is the point 0, 1. All of these exponential functions have this point in them until we start messing with a, until we start messing with the initial value. And the point at x equals 1, well, that would be way up here at 27. This is the point. This is the point. This is the point 127. Okay, so we were asked to find, what will this be at 2/3? Well, it turns out that at 2/3, that's the point 2 over 3 is x, and the y is 9. All right, so it's well down from this 27, but it's between 1 and 27. That's all I'm trying to show you. It's a part of the curve. So you want to start thinking about these curves. It really helps your visual understanding of these ideas. Okay, convert 4 and 16 to rational form. All right, so this is not so bad. We're just going to have 16 to the 3 over 4. Okay, and that's going to be equal to the 4th root of 16, which is 2, raised to the power 3, which is 8. Okay, this is 2 to the 3. Why? Because 16 to the 1 over 4 equals 2. This is some number when multiplied by itself 4 times gives me this number. 2 to the 4 is 16. 2 raised to the power 3 now is 8. That's how you answer these types of questions. Okay, solving. Solve each of the following. 36 to the 3 over 2. Okay, well, I can write that as 36, but I want the square root of that, and then I'm going to raise that to the power 3, and so that's equal to 6 to the 3. That's equal to 216. Done. Final answer for this one. All right, and now let's change colors because I like blue, and I like to be able to draw. 27 to the 4 over 3. We're looking for a number a little bigger than 27. Okay. This we're looking for a number a little bigger than 36. We got one. It's a little bit bigger. Okay. As far as exponentials go, that's only a little bit bigger. And here, 27 to the 4/3. Well, we can write that as 27, but the third root of it. Okay. And we're going to raise that to the power 4. I don't do this, but I'm just doing it right now to show you. Okay. And then that's equal to, well, the third root of 27 is 3. Some number multiplied by itself 3 times will give you 27. That's 3. Okay, 3 raised to the power 4, it's 81. 3 to the 4 equals 81. Now, I don't write this. I never write that. I would just do it in my head, but what I would do if I wanted to break it up is I would do this. 27 to the 1/3, I would write it that way, raised to the power 4. Notice, power of a power rule here applies. We were reviewing that just before with exponential expressions. X to the A to the B equals x to the a times b? Well, here 27 to the 1/3 times 4. 1/3 times 4 is 4/3. So you can break these things up this way and see it much more clearly to answer these types of questions. Okay, rational exponents and the exponent laws. All right, so here, 64 to the negative 1/2. Okay, taking the 1/2 power of something is the same thing as taking the square root. Square root of 64 is something times itself gives me 64 is 8. 8 times itself gives me 64. So this is equal to, well, first of all, it's equal to 1 over 64 to the 1/2, which is equal to 1 over 8. Okay, that's what it is. Now, 1/8 to the negative 1/3 is just 2. Okay, it's just like you will get to the point where you just look at these and you answer them in your head very quickly. Okay, so here it means flip the fraction. That's what this means, flip the fraction. So this is the same thing as 8 to the 1/3. I just got rid of the negative and I flipped this fraction. So that's that. And then the third root of 8 is 2. Okay, so that's how you do those. Now, if you want to solve for the base in an exponential term, this is going to dovetail nicely into exponential decay and growth. Okay, if you have an equation that looks like this, the initial value of a car was $10,000, and it was depreciating by some value every year. It was losing some percentage of its value, and such that after 5 years, it was only worth a fifth of what it had cost before. Okay, so then what you would be solving is I would divide both sides by 10,000, and I would get 1/5 on that time. 2,000 divided by 10,000 is 1/5. That's equal to b raised to the power 5. So that is like saying I am looking for some number that when multiplied by itself 5 times gives me 1 over 5. Seems like an easy question. I don't know how to do that. My head's really hard. So what you would do is you can take the 1 over 5 power of both sides. Okay, so you can use the reciprocal of this power and take that of both sides. So you would have 1 over 5 to the power 1 over 5 is equal to b to the 5 to the 1 over 5. Okay, now here, 5 times 1 over 5 is 1. That's why you do that, because that will give you, that will solve for b on this side. And then 1/5 to the 1/5, well, you can punch that on your calculator. And it looks like, I should use the keyboard here. 1 over 5. I have a fractions button somewhere. I never use a fractions button. It's just 1 over 5 raised to the power. Where's my raised to the power button? Here it is. Raised to the power, put it in brackets, 1 divided by 5 brackets. So that's 0.2. No, wait, no, equals. There we go. Yeah, there. And then it's 72.4. 0.724. So this is a car that's losing a little bit more than 25% of its value every year. How'd you know that, Mr. Jennings? Well, because if it was 1, it was 1.0, that would mean every year it has 100% of its value, never loses value. It's lower than 1. It's lower than 1 by a little bit bigger than 2.5, 0.25. It's a little bit bigger than 0.25. It's losing a little more than a quarter of its value every year. If you take this crazy number, multiply it by itself 5 times, you'll get a nice, clean, even 1 over 5. All right. So that is your B. Your B is 0.72 something, something, something. Maybe have a rounding error there. No, I don't even have a rounding error. That's 0.72. Okay. So if I want to solve these for x, I can raise both sides to the power 1/4. X equals 2. Because this 4 times 1 over 4 is x to the 1. And then 16, the fourth root is 2. Okay. X to the 3 halves is equal to 27. Well, that's interesting. Well, that means that x is 9. 9. Yeah. So how do I do that? I take the 2/3 root of each time. X to the 3 over 2 raised to the 2 over 3. Notice I just flipped this fraction. Whatever fraction that is, you flip it. And that gives you 27 to the 2 over 3, which is already a problem we have answered. And that is equal to 27 to the 1/3 raised to the power 2. That's 3 to the 2, that's 9. X equals 9, because this is x to the 1 over here now. Neat, eh? So you just take the reciprocal power of each side, and that's how it solves. So do those questions. Ha ha ha. Okay, so we have a quiz on exponential growth and decay. We have a quiz on rational exponents and exponential expressions tomorrow. All right, so now let's take a look at these exponential growth and decay questions. Okay, so the biggest issue here is identifying the correct growth factor for your different problems. Okay, the growth factor in this equation is very important. What equation? This is what an exponential growth or decay equation looks like. The amount of something after a certain amount of time. Time is going to be a very common variable in these exponential problems. A lot of things progress exponentially over time. Is equal to the initial value. We'll call it, we can call it v for the initial value, multiplied by b, the growth factor, raised to the power t. Okay? These are what the main setup that you want to understand is. This is similar to an A transformation. It's going to stretch all your y values. And then b is part of the parent function, basically. You can basically think of this as part of the parent function. There's not one single parent function for exponentials, although you could always just use 2 to the x and convert it with different transformations, but that's a little bit fancy. Okay, b is an important number to get right. How do we do it? How do we get this growth factor? Well, when you see something like this, here is an example of one of these. It has an initial value of 256. Let's say there are 256 bunnies in Central Park, and every year there's 35% more of them. 35% more of them in Central Park. How do I know it's 35% more? Because this 1.35 was a number that was created this way. 1 plus 0.35. This is 100%, which is if this number stayed the same over time, it would just be 100% every year. Every year there's 100% the same number of bunnies. Okay, there's always 256. But no, these bunnies are growing. They're growing by 35% per year. So you add the growth to this 100%, and that's how you get this number here. Okay, so the initial amount for this one is 256. And then the growth factor is 1.35. That's the growth factor. The percentage increase is 35%, because that's 0.35 as a percent. If you got 99%, it means you got 0.99 of the questions right. Okay, here this one, here the percent increase is only 7%. Okay, because 0.7. Growth factor 1.07, and the initial value is 7.5. Maybe a car is worth $7.5 thousand, and every year it's becoming more valuable. It's some kind of strange antique car that's only worth $7.5 thousand. All right, here, initial amount. Let's build an equation. Y is equal to 548 multiplied by some growth factor, but I want this to be growing at 0.94. That's 9.4% as a decimal. Notice this extra zero moves the 9 into the hundred spot, and this goes into the thousand spot. Okay, 9.4. That's in the thousandths spot if you have a little decimal there, because this decimal move it once, twice, and that's your percent as a decimal. So this is times 1.094 raised to the power x. All right. A rabbit farm originally has 24 rabbits. The population doubles every month. If it doubles every month, then we have 24 rabbits. Double means grow by 100%. So that would be 1 plus 100% as a decimal, 1.00. Okay, it's 2 equals 2. Growth factor here is 2. And every month, so we have let x be the number of months. And so then I have the amount of rabbits is a function of time, which we have called x, and that's the equation. How many rabbits exist after 10 months? So I'm being asked to solve r at 10, and that's equal to 24 multiplied by 2 to the power 10, which is this number here with an extra 6 on it. I happen to remember that. So that's going to give us, when we punch this on our calculator, you have to do BEDMAS correctly. Do the exponent first. 2 raised to the power 10 equals, and then multiply 24576. 24576. Okay, there. You have to do bedness correctly. If you multiply 24 times 2, then this 24 comes along for this ride. You get a very different number. This is 24576. Let's keep going. Okay, a sample of bacteria has 500 cells. After 9 hours, the sample has this many cells. How many bacteria exist after 3 days? So this is a complex question. A lot of bacteria after 3 days. Okay, cool. It only grows by a factor 3 after 9 hours. So this is how you solve this type of question. All right. So here we go. I know that there's going to be some number of bacteria and that it's a function of time. So I'm setting up a function for number of bacteria that's going to have time as its variable. And then I'm going to put in my initial value. I'm not given a growth factor, so call it B. And I know that after 9 hours, I know that, so this is still just T here. I'm just setting up an equation. This has two unknowns, B and T, but I'm given 1 point. After 9 hours, the sample has this many cells. With that point, I can solve for B, and this is how. This is basically saying B at 9 equals 1500. Okay, so I can put that in here. 1500 equals 500 times B raised to the power 9. Okay, so now divide by 500. This tells me 3 is equal to B to the 9. We just looked at taking the 1/9 power of both sides as an inverse operation to get rid of this exponent. So this is 3 to the 1 over 9 equals B. So there it is. That's your B value. And you could even just plug that into your original equation. Sure, no problem. And that would be an exact answer. If you want the decimal answer, I don't know why you would, but here you go. This is 3 raised to the... I could use the nth root, or I can use 3 to the power, put in brackets, 1 divided by 9. And the bracket is, that's the power. And then this is what it is. 1.12. 1.129. Okay, so it's 1.13. It's growing by 13% every hour. Okay, that's not a number that should surprise us. That should feel very correct. That that B would be equal to 1.13. It's approximately equal to that. Okay, I've rounded. And that was after 9 hours they triple. So if every hour they grow by 13%, it might sound a little surprising, but it's true. That actually makes a lot of sense. Once you look at some of these curves, maybe we should graph it. Maybe we should graph the resulting thing and see what's going on, and that will help us. So then what I have now is this function. B of t is equal to 500, the initial number of bacteria, multiplied by 1.13. That's my growth factor raised to the power t. T is hours. All right. So now I'm asked how many bacteria exist after 3 days. 3 days is 72 hours. So B at 72 equals 500 multiplied by 1.13 to the 72. Raising something to the power 72 is not something you want to do as a repeated multiplication. You're going to use your to the y button and go 72 here equals, whoa, it's 6,561 times as big. Okay, so that's, and notice we get a nice round number when I keep that decimal on there. I wonder why that is. I can show you later. What am I looking at? Oh, right. So I have this, and I'm going to multiply that by 500, and that gives me 3,280,500. 3,280,500. Okay, that gives me the right answer. Okay, let's keep going. The population was this, and this, and then this, and it's growing. Okay, so yeah, this is the last problem type that I need to cover. Okay, so this is probably the end of the video. It's already a half-hour video. Okay, so you're still here. Oh my goodness. You could send me an email. Say, Mr. Jennings, I got here, and the secret code word is, we need a fun code word. Marsupial. Okay, if you email me marsupial, I will email you a joke. Okay, so that's a little bonus for anyone that's gotten this far in this video. You also need to know my email address. If you found this video by accident for something, thanks. And here we go. So the population was so the initial value is 420 in 1985. Usually we would set that as year zero. Year zero equals 1985. So it grows by 8% per year. Okay. What will the population be in 2010? So 2010 minus 1985 is equal to 25. So that's year 25. Okay. So that's how I would know that. Well, you can set these up another way, but it's really weird. I don't want to tell you to do that. So this is 420 multiplied by 1.08. Why? Because it's growing by 8% per year. So that's 100% plus 8% raised to the power. Oh, I'm sorry. My initial value is 420. My growth factor, my B, is equal to 1.08. That was what I was doing. And then I can set up my equation. So the population of Nottawa is a function of time, and it's equal to 420, the initial value, multiplied by 1.08 raised to the time, raised to the number of years since 1985. So first question, A. What will the population be in 2010? Well, I'm being asked to solve for P at 25. That's equal to 420. 1.08 raised to the power 25. Okay, so do that. You're going to do that. Oh, hi. Come on in. So let me pause my video here. Come on in, no problem.
Sorry, dude.
That's okay. And we're back. Where were we? Oh, right. We were doing the last problem for today. So here, this is how we would evaluate this one. We have 25 years of 8% growth, which is a very quickly growing city. Let's find out what that is. 1.08 raised to the power 25 equals, yeah, it's almost 7 times as big as 8% growth over 25 years. 8% is a good return on investment for your money. So imagine investing $1,000 and turning that into $7,000 after 25 years. Okay, this is still, you need a good amount of time for that 8% to do its magic, but that's a pretty good amount of magic, right? Like, would you rather have $1,000 now or $7,000 in 25 years? It's a question you can ask yourself, and then put your money where you want it to be. Okay, so anyway, so then we take that and we multiply it by 420. Who made this question? Anyway, and so then the population is going to be 7 times what it was in 1985. It's going to be nearly 3 million. Let's see if we got the right answer. Yeah, we did. Okay, now, when will the population reach 1820? Okay, so here is the type of problem that we have where we have an unknown in our variable. We don't know what t is when the output is 1820. So this is what we know. P at some t, I don't know it yet, is equal to, yeah, oh, you got them?
I am so sorry. Yeah.
Delightful. Thanks so much for taking such great care of us today.
Aw, thank you. These are from Mr. Van Sice's class. Okay.
Okay, great.
Awesome.
Oh, which number is that?
Number 1 and number 2. Oh, Mr. Van Sice. He's the art room.
Okay.
So like where all the big, he's got like this artwork over.
Yeah.
I don't know his number. So.
Okay, thanks. Sorry. So this, we know this is P at t. For some value t is going to be 1820. So 420 is going to grow to 1820 at some point. It's going to be before this year, right? Because this was bigger than that. That gave us 3,000 or so. So it's going to be before that year. And what year will the population reach that? And indeed, it turns out to be. Okay, so how do we find it? Okay, well, you set this equal. You say 1820 is equal to 420 multiplied by 1.08 raised to some number of years. All right? Then you divide away your loose stuff. This is loose. We want to isolate this t as much as possible. We have to observe bedmas, but we can move this multiplication over to the other side, no problem. So 1820 divided by 420 is some ugly number. 18. Hi, Damon. How are you doing?
Good. I got
Good.
that thing done.
Awesome. 4 and a third. If that's 4 and a third.
Anything for it. I still tried to sit all last night.
Cool. Okay. So now I need to find some power of t that when I raise this to it that many times gives me 4 and a third. Two methods. Guess and check. Oh, it's three methods. Algebraic that you'll learn next year. Guess and check that we do. And use Desmos that we can also do. So here's how I would do it in Desmos. I can put this or I can put this, either one. So if I do this in Desmos, I would use 4 and a third. So let's do that over here. Desmos. Hi, Jared.
Good morning.
Good morning. So I have 4.33333. Oh, wait, I can say y is equal to, hold on one moment. No, I'm talking. So 4 and a third. Oh, I could put on my mask now. The students are here. 4 and a third. Oh, another student has a question. So y is equal to 1.08 raised to the power x. Bracket in there. There. Just like we would predict, it goes through this 0.01. Okay? It's rising very slowly, but as you see, as I zoom out more and more, it looks very exponential over there. The population, Nottawa is going to have some problems in about 50 years. It's going to, 50 times their population in 50 years. It's pretty cool. Okay, and then I want to know, when does y equal 4 and a third? So I can write 4 and a third as 13 over 3. Over 3. That's 4 and a third. And so there, it's right there. See? 19.053. 19 years. 19 years after 1985, which would be 2004. Okay, so that's how you do that with Desmos. Let's say you don't have access to Desmos and you need to guess and check this. Well, you just create a table. T over there, and you're going to put your guesses down here, and I'm going to guess to start, let's say I guess 30. All right. And then over here, you're going to take 1.08 and raise it to the power t. Okay, so if I'm going to guess 30, then I would have, this is a little anticlimactic doing this after we already know the answer. Raised to the power 30. Oh, that's bigger than 4. Bigger than 4 by a long way. So this was about 10. That's too big. And so now I'm going to guess smaller. Let's guess 10. All right. 1.08 raised to the power 10 equals 2.15. It's too small. Okay, so when I guessed 10, it was 2.1 or 2.2. Okay, it was too small. Okay, so now let's guess in the middle. Let's guess 20. So here, 1.08. And remember, these are useful like numbers. Is 20 years of growth, and that's a pretty reasonable thing to guess. 4.66. Oh, so close. We're feeling like we're Sherlock Holmes and the murderer is near. The answer is very close. This is 4.67 or something like that. Okay, so now test a little smaller than that, and you test 19, and you find that 19 is the right number. Yay! Okay, so that's how you do it. And then you go back to the question, and you say, okay, 1985 plus 19 is 2004. So that's how you do that. Okay, that's how you do it. So yeah, I hope that has been helpful. These are the problem types that we'll be looking at tomorrow on the quiz: exponential growth and decay, rational exponents, and exponential expressions. Thanks for hanging with me up until this point. And remember, there's a secret code word inside the video. If you email me this code word, then I will email you a joke. Okay, bye for now, everybody.